Hello everyone, I'm Jusang Oh from ADAS Lab at Seoul National University. Today I'll present Mixture-of-Recursions learning dynamic recursive steps for adaptive token level computation. This paper was posted on arXiv in July and is a collaboration led by researchers at KAIST with collaborators including Google DeepMind. Since its release, it has quickly drawn strong interest across several research communities. Here is today's outline. I start with the motivation, then explain the mixture-of-recursions method, followed by experiments. I'll close with the conclusions and limitations. Let's begin with the motivation. The paper frames efficiency for LLMs along two axes. First, parameter efficiency, reduce or sharing weights. For example, in a recursive transformer, multiple layers share the same parameters, so you can view the stack as repeatedly applying a single block. A second one is adaptive computation, and it spans compute more only where needed. A classic example is early exiting, where tokens exit once sufficient confidence is reached, skipping deeper layers. A natural question is, can we combine both axes in one model? Concretely, in a recursive transformer, can each token's number of recursions be decided dynamically? Prior work often avoided dynamic recursion depth due to performance degradation and KB cache inconsistencies, defaulting to fixed recursion depth. This work addresses both issues, stable dynamic routing of recursion depth and a KB sharing scheme that remains consistent. Now I'll introduce the mixture-of-recursions framework. Consider a model with 6 total layers arranged as 3 recursion blocks. There are two ways to unroll recursion. The first one is cycle strategy. It passes through different layers once, then repeat that cycle. The second one is sequence strategy. It fully reuses one layer for several recursions, then moves to the next layer. In a standard transformer, token T's hidden state is updated by layer. In the recursive versions, the layer index orders changes according to cycle or sequences. There's also a middle variant that keeps unique first and last layers, sharing only the middle part. Combining these gives 4-parameter sharing strategies: cycle, sequence, middle cycle, and middle sequence. Here's the MOR overview. Relative to a basic recursive transformer, the key change is that each token can take a different number of recursion steps. Or rather, at each recursion block decides whether a token continues or exits, so different tokens ends up with different depths. MOR proposes two routing strategies to decide a token's recursion depth. The first one is expert choice routing. Each recursion step acts like an expert. As step R, the router computes a gate score for each token. Only tokens above a threshold get updated and proceed. Across steps, this yields a top K cascade with progressively fewer tokens. And the second one is token choice routing. Instead of deciding at each step, the router uses the token's initial hidden state to compute scores for all experts at once. The token is then assigned a target depth, and it recurses up to that depth. There's a few more details in router. In expert choice, training sees future information, but inference does not, so it creates a train-test mismatch. The authors mitigate this with an auxiliary loss and auxiliary router that teaches the router to make inference time decisions reliably. So in more detail, the auxiliary router is an additional lightweight network trained jointly but used only during inference. And it predicts whether a token will be among the top case selection. Auxiliary loss is on BCE loss to the main router itself, enabling it to simultaneously learn to push top K tokens towards 1 and others towards 0 during training. And in token choice, tokens can become unbalanced across depths. A balancing loss encourages uneven distribution to keep compute predictable and stable. Next is KV caching. So MR uses two strategies. The first one is recursion-wise KV caching. At each recursion step, only the selected tokens cache their KV, and attention is restricted to those entries. This reduces KV memory roughly to 1 over 2 of vanilla, and attention flops to about square of k over n. And the second one is recursive KV sharing. So the cache only at the first recursion and you reuse that KV for later recursions. This drops KV memory to about 1 over n and reduces attention cost to about k over n. And with recursive KV sharing, KV usage exhibits a periodic pattern across recursion steps because later steps reuse the first step's KV. You also observe periodic similarity in keys and values, supporting why sharing can work with limited quality loss. Now the experiments. The authors pre-trained llama-based models from scratch using small LM styles configurations on the fine web edu corpus, then evaluate on 6 few-shot benchmarks in addition to validation loss. And there's main results, and there's two takeaways. The first one is under equal training flops, more outperforms baselines with fewer parameters. And the second one is at equal parameter counts, MOR which is better performance with less compute than the baseline. As the model size increases, MOR's loss versus compute curve improves more steeply than baselines. So this suggests MOR is a more scalable and parameter efficient architecture. Throughput also improves thanks to continuous depth-wise batching and early exiting. Throughput increases as the allowed max recursion grows. Here's an inference examples. Tokens assigned lower depth exit early, while more important tokens receive deeper recursion, illustrating adaptive token level compute. Now the ablation studies. For routing strategy, in expert choice, the best configuration uses a linear router with a sigmoid gate and an auxiliary loss. In token choice, adding a balancing loss yields more stable routing and better overall performance than loss-free variants. For KB sharing, MOR remains robust even with parameter sharing. Although sharing can slightly hurt accuracy, it brings meaningful memory and latency gains and works reliably across architectures. Regarding max recursion depth, increasing the permitted depth enables test time scaling. You can trade more recursion for better log likelihood and inference. Conclusions and limitations. So there are three conclusions. So first, MR unifies three efficiency levers in one architecture: parameter sharing, adaptive token level recursion, and KV efficient caching. The second one is that MR reduces both quadratic attention computation and redundant memory access costs. Lastly, MR improves our average official accuracy even with higher inference throughput. And there are 5 limitations. First one is reasoning adaptation. MR has not yet been fine-tuned on reasoning tasks, and future work should align recursion depth with reasoning complexity through advanced routing. Second one is scaling constraints. So current experiments are limited to models up to 1.7 billion parameters, and scaling MR to larger models remains an open direction. Third one, the limited capacity flexibility. So the expert choice routing produces rigid router outputs after training, so making it difficult to adjust computation capacity at inference time. And lack of integration with sparse techniques. MR has not been combined with structured sparsity or pruning, which could further reduce computation and improve efficiency. Lastly, there are modality limitation. MR is currently applied only to text, and future work should explore its extension to vision, audio, and multimodal domains. So that concludes my talk. Thank you for your listening. I'm happy to take questions in the comments.